Personal Rapid Transit, also called POD-car, is a public transport mode featuring small automated vehicles operating on a network of specially built guideways. PRT is a type of automated guideway transit, a class of system which also includes larger vehicles all the way to small subway systems. PRT vehicles are sized for individual or small group travel, typically carrying no more than 3 to 6 passengers per vehicle. Guideways are arranged in a network topology, with all stations located on sidings, and with frequent merge-diverge points. This allows for non-stop, point-to-point travel, bypassing all intermediate stations. The point-to-point service has been compared to a taxi or a horizontal lift. As of July 2013, 4 PRT systems are operational. The world's oldest and most extensive PRT system is in Morgantown, West Virginia. It has been in continuous operation since 1975. Colloquially known merely as the PRT, West Virginia University's system moves student and visitors alike to a number of popular destinations throughout the city. Since 2010, a 10-vehicle two-gauge tire system has operated at Masdar City, UAE, and since 2011 a 21-vehicle ultra-port system has run at London Heathrow Airport. A 40-vehicle vector system with inline stations officially opened in Suncheon, South Korea, in April 2014 after a year of testing. Expansion of the Masdar system was cancelled just after the pilot scheme opened. Numerous other PRT systems have been proposed but not implemented, including many substantially larger than those now operating. Overview: most mass transit systems move people in groups over scheduled routes. This has inherent inefficiencies. For passengers, time is wasted by waiting for the next arrival, indirect routes to their destination, stopping for passengers with other destinations, and often confusing or inconsistent schedules. Slowing and accelerating large waits can undermine public transport's benefit to the environment while slowing other traffic. Personal rapid transit systems attempt to eliminate these wastes by moving small groups non-stop in automated vehicles on fixed tracks. Passengers can ideally board a pod immediately upon arriving at a station, and can with a sufficiently extensive network of tracks take relatively direct routes to their destination without stops. Perhaps most importantly, PRT systems offer many traits similar to automobiles. For example, they offer privacy and the ability to choose one's own schedule. PRT may in fact allow for quicker transportation than cars during rush hour, since automated vehicles avoid unnecessary slowing. A PRT system can also transport freight. The low weight of PRT's small vehicles allows smaller guideways and support structures than mass transit systems like light rail. The smaller structures translate into lower construction costs, smaller easements, and less visually obtrusive infrastructure. As it stands, a citywide deployment with many lines and closely spaced stations, as envisioned by proponents, has yet to be constructed. Past projects have failed because of financing, cost overruns, regulatory conflicts, political issues, misapplied technology, and flaws in design, engineering or review. However, the theory remains active. For example, from 2002 to 2005, the EDICT project, sponsored by the European Union, conducted a study on the feasibility of PRT in 4 European cities. The study involved 12 research organizations, and concluded that PRT would provide future cities a highly accessible, user-responsive, environmentally friendly transport system which offers a sustainable and economic solution. Could cover its operating costs, and provide a return which could pay for most, if not all, of its capital costs. Would provide a level of service which is superior to that available from conventional public transport. Would be well received by the public, both public transport and car users. The report also concluded that, despite these advantages, public authorities will not commit to building PRT because of the risks associated with being the first public implementation. The PORT acronym was introduced formally in 1978 by J. Edward Anderson. The Advanced Transit Association, a group which advocates the use of technological solutions to transit problems, compiled a definition in 1988 that can be seen here. List of operational ATN systems. Currently, 5 advanced transit network systems are operational, and several more are in the planning stage. List of automated transit network suppliers. The following list summarizes several well-known automated transit networks suppliers as of 2014. Revenue Service, Boeing, Ultra, 2GH Air, WGH, Vectus. Full Test Track, Moditram, Intamin, Induct, Cabine Torxi. Mock-ups or scale models, Taxi 2000, SkyCab, MoveMile, ECO Mobility, Cybertran, SHWEEB, TubeNet Transit Systems. Analyzed and stimulated, TriTrack, SkyTran, PRT International, GTS Foundation, Beamways, Mr. Conceptus, SkySabs, Minnesota Port, JPODS, BM Design, Interstate Traveler, Flyway, AUF, ECOPRT, Skyride, APGM. Historical, CVS, Aramis, PRT 2000, Monocabaro MAG. History. Origins. Modern port concepts began around 1953 when Don Fichter, a city transportation planner, began research on PRT and alternative transportation methods. In 1964, Fichter published a book which proposed an automated public transit system for areas of medium to low population density. One of the key points made in the book was Fichter's belief that people would not leave their cars in favor of public transit unless the system offered flexibility and end-to-end transit times that were much better than existing systems. Flexibility and performance he felt only a PRT system could provide. Several other urban and transit planners also wrote on the topic and some early experimentation followed, but PRT remained relatively unknown. Around the same time, Edward Holtham was studying monorail systems. Holtham noticed that the time to start and stop a conventional large monorail train, like those of the Wuppertal-Schwebebahn, meant that a single line could only support between 20 and 40 vehicles an hour. In order to get reasonable passenger movements on such a system, the trains had to be large enough to carry hundreds of passengers. This, in turn, demanded large guideways that could support the weight of these large vehicles, driving up capital costs to the point where he considered them unattractive. Holtham turned his attention to developing a system that could operate with shorter timings, thereby allowing the individual cars to be smaller while preserving the same overall route capacity. Smaller cars would mean less weight at any given point, which meant smaller and less expensive guideways. To eliminate the backup at stations, the system used offline stations that allowed the mainline traffic to bypass the stopped vehicles. He designed the monocab system using 6 passenger cars suspended on wheels from an overhead guideway. Like most suspended systems, it suffered from the problem of difficult switching arrangements. Since the car rode on a rail, switching from one path to another required the rail to be moved, a slow process that limited the possible headways. UMTA is formed. By the late 1950s the problems with urban sprawl were becoming evident in the United States. When cities improved roads and the transit times were lowered, suburbs developed at ever-increasing distances from the city cores, and people moved out of the downtown areas. Lacking pollution control systems, the rapid rise in car ownership and the longer trips to and from work were causing significant air quality problems. Additionally, movement to the suburbs led to a flight of capital from the downtown areas, one cause of the rapid urban decay seen in the U.S. Mass transit systems were one way to combat these problems. Yet during this period, the federal government was feeding the problems by funding the development of the interstate highway system, while at the same time funding for mass transit was being rapidly scaled back. Public transit ridership in most cities plummeted. In 1962, President John F. Kennedy charged Congress with the task of addressing these problems. These plans came to fruition in 1964, when President Lyndon B. Johnson signed the Urban Mass Transportation Act of 1964 into law, thereby forming the Urban Mass Transportation Administration. the UMTA was set up to fund mass transit developments in the same fashion that the earlier Federal Aid Highway Act of 1956 had helped create the interstate highways. That is, the UMTA would help cover the capital costs of building out new infrastructure. PRT research starts equals. However, planners who were aware of the PRT concept were worried that building more systems based on existing technologies would not help the problem, as Fisher had earlier noted. Proponents suggested that systems would have to offer the flexibility of a car. The reason for the sad state of public transit is a very basic one: the transit systems just do not offer a service which will attract people away from their automobiles. Consequently, their patronage comes very largely from those who cannot drive either because they are too young, too old, or because they are too poor to own and operate an automobile. Look at it from the standpoint of a commuter who lives in a suburb and is trying to get to work in the central business district. If he is going to go by transit, a typical scenario might be the following: he must first walk to the closest bus stop, let us say a 5 or 10-minute walk, and then he may have to wait up to another 10 minutes, possibly in inclement weather, for the bus to arrive. When it arrives, he may have to stand unless he is lucky enough to find a seat. The bus will be caught up in street congestion and move slowly, and it will make many stops completely unrelated to his trip objective. The bus may then let him off at a terminal to a suburban train. Again he must wait, and, after boarding the train, again experience a number of stops on the way to the CBD, and possibly again he may have to stand in the aisle. He will get off at the station most convenient to his destination and possibly have to transfer again onto a distribution system. It is no wonder that in those cities where ample inexpensive parking is available, most of those who can drive do drive. In 1966, the United States Department of Housing and Urban Development was asked to undertake a project to study new systems of urban transportation that will carry people and goods speedily, safely, without polluting the air, and in a manner that will contribute to sound city planning. The resulting report was published in 1968 and proposed the development of PRT, as well as other systems such as dial-a-bus and high-speed interurban links. In the late 1960s, the Aerospace Corporation, an independent non-profit corporation set up by the U.S. Congress, spent substantial time and money on PRT, and performed much of the early theoretical and systems analysis. However, this corporation is not allowed to sell to non-federal government customers. In 1969, members of the study team published the first widely publicized description of PRT in Scientific American. In 1978 the team also published a book. These publications sparked off a sort of the transit race in the same sort of fashion as the space race, with countries around the world rushing to join what appeared to be a future market of immense size. The oil crisis of 1973 made vehicle fuels more expensive, which naturally interested people in alternative transportation. System developments In 1967, aerospace giant Matra started the Aramis project in Paris. After spending about 500 million francs, the project was cancelled when it failed its qualification trials in November 1987. The designers tried to make Aramis work like a virtual train, but control software issues caused cars to bump unacceptably. The project ultimately failed. Between 1970 and 1978, Japan operated a project called Computer-Controlled Vehicle System. In a full-scale test facility, 84 vehicles operated at speeds up to 60 km per hour on a 4.8 km guideway. 1 second headways were achieved during tests. Another version of CVS was in public operation for 6 months from 1975 to 1976. This system had 12 single-mode vehicles and 4 dual-mode vehicles on a 1.6 km track with 5 stations. This version carried over 800,000 passengers. CVS was cancelled when Japan's Ministry of Land, Infrastructure and Transport declared it unsafe under existing rail safety regulations, specifically in respect of braking and headway distances. On March 23, 1973, U.S. Urban Mass Transportation Administration Administrator Frank Herringer testified before Congress, a DOT program leading to the development of a short, 1/2 to 1 second headway, high-capacity PRT system will be initiated in fiscal year 1974. However, this HCPRT program was diverted into a modest technology program. According to PRT supporter J. Edward Anderson, this was because of heavy lobbying from interests fearful of becoming irrelevant if a genuine PRT program became visible. From that time forward, people interested in HCPRT were unable to obtain UMTA research funding. In 1975, the Morgantown Personal Rapid Transit project was completed. It has 5 offline stations that enable non-stop, individually programmed trips along an 8.7-mile track serviced by a fleet of 71 cars. This is a crucial characteristic of PRT. However, it is not considered a PRT system because its vehicles are too heavy and carry too many people. When it carries many people, it operates in a point-to-point fashion, instead of running like an automated people mover from one end of the line to the other. During periods of low usage, all cars make a full circuit, stopping at every station in both directions. Morgantown Port is still in continuous operation at West Virginia University in Morgantown, West Virginia, with about 15,000 riders per day. It successfully demonstrates automated control, but was not sold to other sites because the steam-heated track has proven too expensive for a system that requires an operation and maintenance budget of $5 million annually. From 1969 to 1980, Mannesmann DMAG and MBB cooperated to build the Cabin-Taxi urban transportation system in Germany. Together the firms formed the Cabin-Taxi joint venture. They created an extensive PRT technology that was considered fully developed by the German government and its safety authorities. The system was to have been installed in Hamburg, but budget cuts stopped the proposed project before the start of construction. With no other potential projects on the horizon, the joint venture disbanded, and the fully developed PRT technology was never installed. Cabin-Taxi Corporation, a U.S.-based company, obtained the technology in 1985, and remains active in the private sector market for transportation systems. Later developments in the 1990s, Raytheon invested heavily in a system called PRT 2000, based on technology developed by J. Edward Anderson at the University of Minnesota. Raytheon failed to install a contracted system in Rosemont, Illinois, near Chicago, when estimated costs escalated to $50 million per mile, allegedly due to design changes that increase the weight and cost of the system relative to Anderson's original design. In 2000, rights to the technology reverted to the University of Minnesota, and were subsequently purchased by Taxi 2000. In 2002, two Getcher-operated 25 4-passenger cybercabs at Holland's 2002 Floriade Horticultural Exhibition. These transported passengers along a track spiraling up to the summit of Big Spotters Hill. The track was approximately 600 meters long and featured only 2 stations. The 6-month operations were intended to research the public acceptance of PRT-like systems. The cybercab as designed for the exhibition was very open. It was comparable to a neighborhood electric vehicle, except it steered itself using magnetic guidance points embedded in the pavement. Ford Research proposed a dual-mode system called PRISM. It would use public guideways with privately purchased but certified dual-mode vehicles. The vehicles would weigh less than 600 kilograms. Most energy use occurs on highways, so small, elevated guideways would inductively power highway use and recharge batteries for off-guideway use. Central computers could do routing. In January 2003, the prototype Ultra system in Cardiff, Wales, was certified to carry passengers by the UK Railway Inspectorate on a 1-kilometre test track. Ultra was selected in October 2005 by BAA plc for London's Heathrow Airport. Since May 2011, a 3-station system has been open to the public, transporting passengers from a remote parking lot to Terminal 5. In May 2013, Heathrow Airport Limited included in its draft 5-year master plan a scheme to use the PRT system to connect Terminal 2 and Terminal 3 to their respective business car parks. The proposal was not included in the final plan due to spending priority given to other capital projects and has been deferred. In June 2006, a Korean-Swedish consortium, Vectors Limited, started constructing a 400m test track in Uppsala, Sweden. This test system was presented at the 2007 Podcast City conference in Uppsala. A 40-vehicle, 2-station, 4.46 km system called SkyCube was opened in Suncheon, South Korea, in April 2014. The Vectors project was based on the Fornebu-Oslo Port project. At the time, the urban development area around Telenor's new headquarters was subject to intense debates as to various more or less innovative public transport systems. The idea of a PRT came up as a possible local solution as well as a business opportunity. In 2000, the Fornebu-Oslo Port project started as a part of an internal educational exercise within ICT strategy innovation within Telenor ASA, a major ICT corporation. As the poster shows, the student project was later transformed into a fast-working concept, technology and business development project with various industry partners and a project group of around 10. The Korean steel company POSCO joined in, and developed the project further in Uppsala, Sweden, in part through new partners, but with all essential elements from the Fornebu-Oslo Port project, as further industrial or governmental support found in the Oslo area vanished. The poster describes the consortium and main results from the Oslo Port project period. Key persons in this concept development phase were, as to technology and operational features development, Enmar Andresen, GAR Paragraph Tuborg, Sweden. Jan Orson, Independent Traffic Planner, Oslo. Alan Forster, Force Limited, Great Britain. And Andrew Howard, HWG Limited, Great Britain. Beyond the general conceptual description, the ICT systems were developed by Noventus AB and others at later stages. In 2007, the Polish port system Masdar was prototyped, and permission was given to install it in 2 Polish cities. Masdar is a typical overhead PRT system engineered for economical aerial reuse of streets rights-of-way, that still gives ground-level access to wheelchairs and freight. System design. Among the handful of prototype systems there is a substantial diversity of design approaches, some of which are controversial. Vehicle design vehicle weight influences the size and cost of a system's guideways, which are in turn a major part of the capital cost of the system. Larger vehicles are more expensive to produce, require larger and more expensive guideways, and use more energy to start and stop. If vehicles are too large, point-to-point routing also becomes more expensive. Against this, smaller vehicles have more surface area per passenger, and larger motors are generally more efficient than smaller ones. The number of riders who will share a vehicle is a key unknown. In the US, the average car carries 1.16 persons, and most industrialized countries commonly average below 2 people. Not having to share a vehicle with strangers is a key advantage of private transport. Based on these figures, some have suggested that 2 passengers per vehicle, or even a single passenger per vehicle is optimum. Other designs use a car for a model, and choose larger vehicles, making it possible to accommodate families with small children, riders with bicycles, disabled passengers with wheelchairs, or a pallet or 2 of freight. Propulsion. All current designs are powered by electricity. In order to reduce vehicle weight, power is generally transmitted via line-side conductors rather than using onboard batteries. According to the designer of SkyWeb Taxi 2000, J. Edward Anderson, the lightest system is a linear induction motor on the car, with a stationary conductive rail for both propulsion and braking. LIMs are used in a small number of rapid transit applications, but most designs use rotary motors. Most such systems retain a small onboard battery to reach the next stop after a power failure. Ultra uses onboard batteries, recharged at stops. This increases the safety, and reduces the complexity, cost and maintenance of the guideway. As a result, a street-level Ultra guideway resembles a sidewalk with curbs and is very inexpensive to construct. Ultra resembles a small automated electric car, and uses similar components. Switching. Most designers avoid track switching, instead advocating vehicle-mounted switches or conventional steering. Those designers say that vehicle switching permits faster switching, so vehicles can be closer together. It also simplifies the guideway, makes junctions less visually obtrusive and reduces the impact of malfunctions, because a failed switch on one vehicle is less likely to affect other vehicles. Other designers point out that track switching simplifies the vehicles, reducing the number of small moving parts in each car. Track switching replaces in-vehicle mechanisms with larger track-moving components that can be designed for durability with little regard for weight or size. Track switching greatly increases headway distance. A vehicle must wait for the previous vehicle to clear the track, for the track to switch and for the switch to be verified. If the track switching is faulty, vehicles must be able to stop before reaching the switch, and all vehicles approaching the failed junction would be affected. Mechanical vehicle switching minimizes inter-vehicle spacing or headway distance, but it also increases the minimum distances between consecutive junctions. A mechanically switching vehicle, maneuvering between two adjacent junctions with different switch settings, cannot proceed from one junction to the next. The vehicle must adopt a new switch position, and then wait for the in-vehicle switch's locking mechanism to be verified. If the vehicle switching is faulty, that vehicle must be able to stop before reaching the next switch, and all vehicles approaching the failed vehicle would be affected. Conventional steering allows a simpler track consisting only of a road surface with some form of reference for the vehicle's steering sensors. Switching would be accomplished by the vehicle following the appropriate reference line. Maintaining a set distance from the left roadway edge would cause the vehicle to diverge left at a junction, for example. Infrastructure design equals guideways. There is some debate over the best type of guideway. Proposals include beams similar to monorails, bridge-like trusses supporting internal tracks, and cables embedded in a roadway. Most designs put the vehicle on top of the track, which reduces visual intrusion and cost as well as easing ground-level installation. An overhead track is necessarily higher, but may also be narrower. Most designs use the guideway to distribute power and data communications, including to the vehicles. The Morgantown port failed its cost targets because of its steam-heated track, so most proposals plan to resist snow and ice in ways that should be less expensive. Masdar's system has been limited because it attempted to dedicate ground level to PRT guideways. This led to unrealistically expensive buildings and roads. Stations. Proposals usually have stations close together, and located on side tracks so that through traffic can bypass vehicles picking up or dropping off passengers. Each station might have multiple berths, with perhaps one-third of the vehicles in a system being stored at stations waiting for passengers. Stations are envisioned to be minimalistic, without facilities such as restrooms. For elevated stations, an elevator may be required for accessibility. At least one system, Masdar, provides wheelchair and freight access by using a cogway in the track, so that the vehicle itself can go from a street-level stop to an overhead track. Some designs have included substantial extra expense for the track needed to decelerate to and accelerate from stations. In at least one system, Aramis, this nearly doubled the width and cost of the required right-of-way and caused the non-stop passenger delivery concept to be abandoned. Other designs have schemes to reduce this cost, for example merging vertically to reduce the footprint. When user demand is low, surplus vehicles could be configured to stop at empty stations at strategically placed points around the network. This enables an empty vehicle to quickly be dispatched to wherever it is required, with minimal waiting time for the passenger. Operational characteristics equals headway distance. Spacing of vehicles on the guideway influences the maximum passenger capacity of a track, so designers prefer smaller headway distances. Computerized control theoretically permits closer spacing than the 2-second headways recommended for cars at speed, since multiple vehicles can be braked simultaneously. There are also prototypes for automatic guidance of private cars based on similar principles. Very short headways are controversial. The UK Railway Inspectorate has evaluated the Ultra design and is willing to accept 1-second headways, pending successful completion of initial operational tests at more than 2 seconds. In other jurisdictions, existing rail regulations apply to PRT systems. These typically calculate headways in terms of absolute stopping distances, which would restrict capacity and make PRT systems unfeasible. No regulatory agency has yet endorsed headways below 1 second, although proponents believe that regulators may be willing to reduce headways as operational experience increases. Capacity port is usually proposed as an alternative to rail systems, so comparisons tend to be with rail. PRT vehicles seat fewer passengers than trains and buses, and must offset this by combining higher average speeds, diverse routes, and shorter headways. Proponents assert that equivalent or higher overall capacity can be achieved by these means. Single line capacity with 2-second headways and 4-person vehicles, a single PRT line can achieve theoretical maximum capacity of 7,200 passengers per hour. However, most estimates assume that vehicles will not generally be filled to capacity, due to the point-to-point nature of PRT. At a more typical average vehicle occupancy of 1.5 persons per vehicle, the maximum capacity is 2,700 passengers per hour. Some researchers have suggested that rush hour capacity can be improved if operating policies support ride-sharing. Capacity is inversely proportional to headway. Therefore, moving from 2-second headways to 1-second headways would double PRT capacity. Half-second headways would quadruple capacity. Theoretical minimum PRT headways would be based on the mechanical time to engage brakes, and these are much less than a half-second. Although no regulatory agency has as yet approved headways shorter than 2 seconds, researchers suggest that high-capacity PRT designs could operate safely at half-second headways. Using the above figures, capacities above 10,000 passengers per hour seem in reach. In simulations of rush hour or high-traffic events, about 1/3 of vehicles on the guideway need to travel empty to resupply stations with vehicles in order to minimize response time. This is analogous to trains and buses traveling nearly empty on the return trip to pick up more rush hour passengers. Grade-separated light rail systems can move 15,000 passengers per hour on a fixed route, but these are usually fully grade-separated systems. Street-level systems typically move up to 7,500 passengers per hour. Heavy rail subways can move 50,000 passengers per hour. As with PRT, these estimates depend on having enough trains. Neither light nor heavy rail scales well for off-peak operation. Networked port capacity The above discussion compares line or corridor capacity and may therefore not be relevant for a networked PRT system, where several parallel lines carry traffic. In addition, Muller estimated that while PRT may need more than one guideway to match the capacity of a conventional system, the capital cost of the multiple guideways may still be less than that of the single guideway conventional system. Thus comparisons of line capacity should also consider the cost per line. PRT systems should require much less horizontal space than existing metro systems, with individual cars being typically around 50% as wide for side-by-side seating configurations, and less than 33% as wide for single-file configurations. This is an important factor in densely populated, high-traffic areas. Travel speed: for a given peak speed, non-stop journeys are about 3 times as fast as those with intermediate stops. This is not just because of the time for starting and stopping. Scheduled vehicles are also slowed by boardings and exits for multiple destinations. Therefore, a given PRT seat transports about 3 times as many passenger miles per day as a seat performing scheduled stops. So port should also reduce the number of needed seats threefold for a given number of passenger miles. While a few PRT designs have operating speeds of 100 km per hour, and one as high as 241 km per hour, most are in the region of 40–70 km per hour. Rail systems generally have higher maximum speeds, typically 90–130 km per hour and sometimes well in excess of 160 km per hour, but average travel speed is reduced about threefold by scheduled stops and passenger transfers. Ridership attraction: if port designs deliver the claimed benefit of being substantially faster than cars in areas with heavy traffic, Simulations suggest that PRT could attract many more car drivers than other public transit systems. Standard mass transit simulations accurately predict that 2% of trips will switch to trains. Similar methods predict that 11% to 57% of trips would switch to PRT, depending on its costs and delays. Control algorithms. The typical control algorithm places vehicles in imaginary moving slots that go around the loops of track. Real vehicles are allocated a slot by trackside controllers. Traffic jams are prevented by placing north-south vehicles in even slots, and east-west vehicles in odd slots. At intersections, the traffic in these systems can interpenetrate without slowing. On-board computers maintain their position by using a negative feedback loop to stay near the center of the commanded slot. Early port vehicles measured their position by adding up the distance using odometers, with periodic checkpoints to compensate for cumulative errors. Next-generation GPS and radio location could measure positions as well. Another system, pointer-following control, assigns a path and speed to a vehicle, after verifying that the path does not violate the safety margins of other vehicles. This permits system speeds and safety margins to be adjusted to design or operating conditions, and may use slightly less energy. The maker of the ultra-port system reports that testing of its control system shows lateral accuracy of 1 cm, and docking accuracy better than 2 cm. Safety. Computer control eliminates errors from human drivers, so PRT designs in a controlled environment should be much safer than private motoring on roads. Most designs enclose the running gear in the guideway to prevent derailments. Grade-separated guideways would prevent conflict with pedestrians or manually controlled vehicles. Other public transit safety engineering approaches, such as redundancy and self-diagnosis of critical systems, are also included in designs. The Morgantown system, more correctly described as a group rapid transit type of automated guideway transit system, has completed 110 million passenger miles without serious injury. According to the U.S. Department of Transportation, AGT systems as a group have higher injury rates than any other form of rail-based transit, though still much better than ordinary buses or cars. More recent research by the British company Ultraport reported that AGT systems have a better safety than more conventional, non-automated modes. As with many current transit systems, personal passenger safety concerns are likely to be addressed through CCTV monitoring, and communication with a central command center from which engineering or other assistance may be dispatched. Energy efficiency. The energy efficiency advantages claimed by PRT proponents include two basic operational characteristics of PRT, an increased average load factor, and the elimination of intermediate starting and stopping. Average load factor, in transit systems, is the ratio of the total number of riders to the total theoretical capacity. A transit vehicle running at full capacity has a 100% load factor, while an empty vehicle has 0% load factor. If a transit vehicle spends half the time running at 100% and half the time running at 0%, the average load factor is 50%. Higher average load factor corresponds to lower energy consumption per passenger, so designers attempt to maximize this metric. Scheduled mass transit trades off service frequency and load factor. Buses and trains must run on a predefined schedule, even during off-peak times when demand is low and vehicles are nearly empty. So to increase load factor, transportation planners try to predict times of low demand, and run reduced schedules or smaller vehicles at these times. This increases passengers' wait times. In many cities, trains and buses do not run at all at night or on weekends. PRT vehicles, in contrast, would only move in response to demand, which places a theoretical lower bound on their average load factor. This allows 24-hour service without many of the costs of scheduled mass transit. Ultraport estimates its system will consume 839 British thermal units per passenger mile. By comparison, cars consume 3,496 British thermal units, and personal trucks consume 4,329 British thermal units per passenger mile. Due to PRT's efficiency, Some proponents say solar becomes a viable power source. PRT elevated structures provide a ready platform for solar collectors, therefore some proposed designs include solar power as a characteristic of their networks. For bus and rail transit, the energy per passenger mile depends on the ridership and the frequency of service. Therefore, the energy per passenger mile can vary significantly from peak to non-peak times. In the US, buses consume an average of 4,318 British thermal units passenger mile, transit rail 2,750 British thermal units passenger mile, and commuter rail 2,569 British thermal units passenger mile. Opposition and controversy. Opponents to PRT schemes have expressed a number of concerns. Technical feasibility debate. The Ohio, Kentucky, Indiana Central Loop report compared the Taxi 2000 PRT concept proposed by the Skyloop Committee to other transportation modes. In the Taxi 2000 PRT system, the Loop Study Advisory Committee identified significant environmental, technical and potential fire and life safety concerns and the PRT system was still an unproven technology with significant questions about cost and feasibility of implementation. Skyloop contested this conclusion, arguing that Parsons Brinkerhoff changed several aspects of the system design without consulting with Taxi 2000, then rejected this modified design. Despite the report's concerns regarding the implementation obstacles of PRT, the report did conclude that compared to the other alternatives, PRT offered the most acceptable point-to-point travel times, the most reliable service levels, the highest level of frequency of service and geography coverage, and was most able to maintain schedule. The report further concluded that, compared to the other alternatives, PRT would have over 3 times the ridership of the next closest alternative, including new transit riders over 9 times higher than the next closest alternative. Vukan Avalik, professor of transportation engineering at the University of Pennsylvania and a proponent of traditional forms of transit, has stated his belief that the combination of small vehicles and expensive guideway makes it highly impractical in both cities and suburbs. According to Avalik, the PRT concept combines 2 mutually incompatible elements of these 2 systems, very small vehicles with complicated guideways and stations. Thus, in central cities, where heavy travel volumes could justify investment in guideways, vehicles would be far too small to meet the demand. In suburbs, where small vehicles would be ideal, the extensive infrastructure would be economically unfeasible and environmentally unacceptable. PRT supporters claim that Avalik's conclusions are based on flawed assumptions. PRT proponent J. E. Anderson wrote, in a rebuttal to Avalik, "I have studied and debated with colleagues and antagonists every objection to PRT, including those presented in papers by Professor Avalik, and find none of substance. Among those willing to be briefed in detail and to have all of their questions and concerns answered, I find great enthusiasm to see the system built." The manufacturers of Ultra acknowledge that current forms of their system would provide insufficient capacity in high-density areas such as central London, and that the investment costs for the tracks and stations are comparable to building new roads, making the current version of Ultra more suitable for suburbs and other moderate capacity applications, or as a supplementary system in larger cities. Regulatory concerns. Possible regulatory concerns include emergency safety, headways, and accessibility for the disabled. Many jurisdictions regulate PRT systems as if they were trains. At least one successful prototype, CVS, failed deployment because it could not obtain permits from regulators. Several port systems have been proposed for California, but the California Public Utilities Commission states that its rail regulations apply to PRT, and these require railway-sized headways. The degree to which CPUC would hold PRT to light rail, and rail fixed guideway safety standards is not clear because it can grant particular exemptions and revise regulations. Other forms of automated transit have been approved for use in California, notably the AirTrain system at SFO. CPUC decided not to require compliance with General Order 143B since AirTrain has no onboard operators. they did require compliance with General Order 164D, which mandates a safety and security plan, as well as periodic on-site visits by an oversight committee. If safety or access considerations require the addition of walkways, ladders, platforms or other emergency disabled access to or egress from PRT guideways, the size of the guideway may be increased. This may impact the feasibility of a PRT system, though the degree of impact would depend on both the PRT design and the municipality. Concerns about PRT research. Wayne D. Cottrell of the University of Utah conducted a critical review of PRT academic literature since the 1960s. He concluded that there are several issues that would benefit from more research, including urban integration, risks of PRT investment, bad publicity, technical problems, and competing interests from other transport modes. He suggests that these issues, while not unsolvable, are formidable, and that the literature might be improved by better introspection and criticism of PRT. He also suggests that more government funding is essential for such research to proceed, especially in the United States. New urbanist opinion. Several proponents of new urbanism, an urban design movement that advocates for walkable cities, have expressed opinions on PRT. Peter Calthorpe and Sir Peter Hall have supported the concept, but James Howard Kunstler disagrees. If we're going to replace the car, why do it with something that's not only like the car, but not really as good as the car? It just seems crazy. He also referred to PRT proponents as a particular kind of crank. Group rapid transit. Group rapid transit is similar to personal rapid transit but with higher occupancy vehicles and grouping of passengers with potentially different origin-destination pairs. In this respect, GRT can be seen as a sort of horizontal elevator. Such systems may have fewer direct-to-destination trips than single-destination PRT but still have fewer average stops than conventional transit, acting more as an automated shared taxi system than a private cab system. Such a system may have advantages over low-capacity PRT in some applications, such as where higher passenger density is required or advantageous. It is also conceivable for a GRT system to have a range of vehicle sizes to accommodate different passenger load requirements, for example at different times of day or on routes with less or more average traffic. Such a system may constitute an optimal surface transportation routing solution in terms of balancing trip time and convenience with resource efficiency. GRT has principally been proposed as a corridor service, where it can potentially provide a travel time improvement over conventional rail or bus and can also interface with PRT systems. However, GRT's necessary grouping of passengers makes it much less attractive in applications with lower passenger density or where few origin-destination pairs are shared among passengers. Automated transit networks is an umbrella term for GRT and PRT. While they have long been considered separate systems, Vectas is developing GRT vehicles formed by combining multiple PRT vehicles. The larger vehicles are designed to accommodate standees and operate on the same guideway as the PRT vehicles. The door spacing of the larger vehicles matches the door spacing of PRT vehicles stopped in a station, allowing the GRT vehicles to share the same station infrastructure too. The concept is intended to allow GRT to serve high-demand station pairs during peak periods, while PRT serves all stations at all times in a network which includes the high-demand station pairs as well as other stations. The same passenger grouping and destinations scheduling approach is used in some advanced elevators, in the form of a destination control system. See also, Duke University Medical Center Patient Rapid Transit, a permanently discontinued personal rapid transit system, Slope Car. References. External links. Will you commute via PRT? Retrieved March 31, 2011, Systems Analysis of Urban Transportation Systems, Scientific American, 1969, 221 27, advancedtransit.org A History of PRT. Personal Rapid Transit book containing papers from the proceedings of the 1973 International Conference on Personal Rapid Transit, Smart Links a website for professionals working with short-distance automated transport. time is wasted by waiting for the next arrival, indirect routes to their destination, stopping for passengers with other destinations, and often confusing or inconsistent schedules. Slowing and accelerating large waits can undermine public transport's benefit to the environment while slowing other traffic. Personal rapid transit systems attempt to eliminate these wastes by moving small groups non-stop in automated vehicles on fixed tracks. Passengers can ideally board a pod immediately upon arriving at a station, and can with a sufficiently extensive network of tracks take relatively direct routes to their destination without stops. Perhaps most importantly, PRT systems offer many traits similar to automobiles. For example, they offer privacy and the ability to choose one's own schedule. PRT may in fact allow for quicker transportation than cars during rush hour, since automated vehicles are in cities. The study involved 12 research organizations, and concluded that PRT would provide future cities a highly accessible, user-responsive, environmentally friendly transport system which offers a sustainable and economic solution. Could cover its operating costs, and provide a return which could pay for most, if not all, of its capital costs. Would provide a level of service which is superior to that available from conventional public transport. Would be well received by the public, both public transport and car users. The report also concluded that, despite these advantages, public authorities will not commit to building PRT because of the risks associated with being the first public implementation. The PORT acronym was introduced formally in 1978 by J. Edward Anderson. The Advanced Transit Association, a group which advocates the use of technological solutions. Personal Rapid Transit, also called PODCAR, is a public transport mode featuring small automated vehicles operating on a network of specially built guideways. PRT is a type of automated guideway transit, a class of system which also includes larger vehicles all the way to small subway systems. PRT vehicles are sized for individual or small group travel, typically carrying no more than 3 to 6 passengers per vehicle. Guideways are arranged in a network topology, with all stations located on sidings, and with frequent merge-diverge points. This allows for non-stop, point-to-point travel, bypassing all intermediate stations. The point-to-point service has been compared to a taxi or a horizontal lift. As of July 2013, 4 PRT systems are operational. The world's oldest and most extensive PRT system is in Morgantown, West Virginia. It has been in continuous operation since 1975. Colloquially known merely as the PRT, West Virginia University's system moves student and visitors alike to a number of popular destinations throughout the city. Since 2010 a 10-vehicle 2-gauge tire system has operated at Masdar City, UAE, and since 2011 a 21-vehicle ultra-port system has run at London Heathrow Airport. A 40-vehicle vector system with inline stations officially opened in Suncheon, South Korea, in April 2014 after a year of testing. Expansion of the Masdar system was cancelled just after the pilot scheme opened. Numerous other PRT systems have been proposed but not implemented, including many substantially larger than those now operating. Overview: most mass transit systems move people in groups over scheduled routes. This has inherent inefficiencies. For passengers, avoid unnecessary slowing. A PRT system can also transport freight. The low weight of PRT's small vehicles allows smaller guideways and support structures than mass transit systems like light rail. The smaller structures translate into lower construction costs, smaller easements, and less visually obtrusive infrastructure. As it stands, a citywide deployment with many lines and closely spaced stations, as envisioned by proponents, has yet to be constructed. Past projects have failed because of financing, cost overruns, regulatory conflicts, political issues, misapplied technology, and flaws in design, engineering or review. However, the theory remains active. For example, from 2002 to 2005, the EDICT project, sponsored by the European Union, conducted a study on the feasibility of PRT in 4 European